Engine block. Cast from iron or aluminum alloy, it's the foundation everything else bolts onto. Inside are the cylinder bores and precisely machined tubes where combustion happens, plus oil passages, coolant channels, and mounting points for nearly every major system in the engine. Modern blocks are mostly aluminum to cut weight while maintaining structural integrity, though heavy-duty and performance applications still lean on cast iron for superior heat resistance. The crankshaft sits at the very bottom, clamped in place by main bearing caps. A cracked or warped block is effectively a death sentence for the engine. It's the part that decides whether you have something worth rebuilding or an expensive paperweight. Cylinders. The cylinders are the tubes inside the block where controlled explosions are converted into motion. Each one is a precisely bored chamber, typically 70 to 100 millimeters in diameter in passenger vehicles, where a piston travels up and down thousands of times per minute. The number of cylinders determines how often power strokes occur per crankshaft revolution. A 4-cylinder delivers 1 power stroke every half rotation. A V8 delivers twice as many. That higher firing frequency is what makes 8-cylinder engines feel smoother at low speed. The cylinder walls are honed with a crosshatch pattern that holds a thin film of oil and helps the piston rings seal, reducing metal-to-metal wear across hundreds of thousands of miles. Cylinder head. Sitting on top of the block, the cylinder head closes off the top of each cylinder and houses most of what governs airflow. The combustion chambers are shaped into its underside, and their geometry directly affects compression ratio and how quickly the flame front travels across the mixture. The head also contains the intake and exhaust ports, the valve seats, the valves themselves, and on modern engines, the camshafts. Spark plug holes are threaded directly into the head. Head design has more influence on engine performance than almost any other single component, which is why cylinder head porting is a common performance modification, and why a warped or cracked head is one of the more expensive repairs in engine rebuilding. Head gasket. Sandwiched between block and head, the head gasket seals 3 systems simultaneously: combustion pressure inside each cylinder, coolant passages, and oil passages, while keeping all 3 completely separate. It operates under temperatures exceeding 200 degrees Celsius and combustion pressures approaching 100 bar. Most modern head gaskets are multi-layer steel, with thin embossed sheets that compress around each cylinder bore under bolt load. When one fails, typically caused by overheating, combustion gases can push into the coolant circuit or coolant can enter the combustion chamber. White smoke from the exhaust as coolant burns is the classic sign. The parts are inexpensive, the labor is not. Pistons. Inside each cylinder, the piston is what physically moves when combustion happens. It travels from top dead center to bottom dead center. The stroke, typically 80 to 90 millimeters, thousands of times per minute. Pistons are machined from aluminum alloy for its lightweight and good thermal conductivity, which helps transfer heat outward through the cylinder walls. The crown, the top face, is shaped to influence how the air-fuel mixture burns. Performance engines use domed or dished crowns to increase compression or improve flame travel. At high RPM, a piston can experience acceleration forces exceeding 1,000 times the force of gravity. Getting the geometry and material right is what separates a component that lasts 200,000 miles from one that cracks under sustained load. If this kind of breakdown is useful to you, hit like and subscribe. More of this coming. Piston rings. 3 thin metal rings sit in grooves around each piston and do separate jobs. The top 2 are compression rings. They seal the gap between piston and cylinder wall, keeping combustion pressure where it belongs rather than leaking past into the crankcase. The bottom ring is the oil control ring, which scrapes excess oil from the cylinder walls on the downstroke and returns it to the sump. Without proper ring seal, compression drops, oil burns, and fuel economy collapses. Rings are typically cast iron or steel, coated with chromium, nitride, or molybdenum for hardness. Ring end gaps are measured in thousandths of an inch. Too tight and thermal expansion locks them up. Too loose, and combustion gases blow past. Connecting rods. The connecting rod links the piston above to the crankshaft below, carrying the full force of combustion every time the cylinder fires. A small end pin connects to the piston at the top. A split big end bolts around the crankshaft journal at the bottom. The rod handles compressive loads on the power stroke and tensile loads on the intake stroke, alternating forces at high frequency. Most rods are forged steel, though performance builds often use titanium or billet aluminum to reduce reciprocating mass. Rod length affects piston dwell time near top dead center, which influences combustion efficiency and how the engine behaves across its RPM range. Crankshaft. This is where linear motion becomes rotation. Each piston pushes down through its connecting rod onto a crank pin, an offset journal on the crankshaft, and that offset converts the straight push into a turning force, exactly like pedaling a bicycle. The crankshaft spans the full length of the engine block, supported by main bearing journals machined to tolerances within thousandths of a millimeter. Crankshaft design, throw distance, counterweight placement, journal sizing directly shapes the engine's power delivery and smoothness. Performance crankshafts are forged from billet steel rather than cast iron, and the highest spec units are machined from a single piece to eliminate any structural weak points. Bearings. Engine bearings are thin half shells of steel backed with a soft alloy, typically copper lead or aluminum-based, that allow the crankshaft and connecting rods to spin with minimal friction. They function on a film of pressurized oil rather than direct metal contact. When oil pressure is adequate, the rotating journal never actually touches the bearing surface. This is called hydrodynamic lubrication, and it's why running an engine without oil for even a few seconds causes catastrophic damage. Main bearings support the crankshaft at the block. Rod bearings sit between each connecting rod and the crankshaft journal. Bearing clearances are measured in thousandths of an inch and are among the most critical tolerances in any engine build. Intake manifold. After air passes through the throttle body, the intake manifold routes and distributes it evenly to each cylinder's intake port. Equal distribution matters. Any imbalance causes some cylinders to run lean and others rich, which hits power, economy, and emissions simultaneously. Runner geometry is where the engineering gets interesting. Longer, narrower runners build intake velocity and favor low RPM torque. Shorter, wider ones favor high RPM flow. Variable intake manifolds, found on most modern performance engines, change runner effective length on the fly based on RPM, capturing the benefits of both. Some builders replace the factory unit with an aftermarket manifold shaped specifically for higher airflow rates. Air filter. Every cubic centimeter of air the engine breathes passes through the air filter first. It removes dust, pollen, and particulates that would otherwise circulate inside the cylinders as abrasive contaminants. A standard paper element is typically rated to catch particles down to around 10 to 15 microns, finer than the eye can resolve. As the element loads with debris, restriction increases and power slowly drops. High-performance aftermarket filters, oiled cotton gauze designs, flow more air than paper and are reusable after cleaning, though they require more discipline about maintenance intervals. In dusty or off-road environments, filter change intervals become critical. Conditions that might load a filter in a few hundred miles are a very different situation from highway driving. Throttle body. The throttle body is a butterfly valve positioned between the air filter and intake manifold that controls how much air enters the engine. Press the accelerator and the plate opens, release it, and the plate nearly closes. Older vehicles connected this mechanically via a cable. Modern engines use electronic throttle control. The pedal sends a signal. The ECU calculates the ideal opening, and an electric motor moves the plate. This allows traction control, cruise control, and idle management to influence throttle position independently of the driver's foot. Throttle body diameter is a common modification on performance engines. A wider bore flows more air at full throttle, though going too large reduces low-speed throttle feel and sharpness. Fuel injectors. Fuel injectors are precision solenoid valves that open for a calculated duration, measured in milliseconds, to spray atomized fuel into the intake port or directly into the combustion chamber. The ECU determines pulse width based on sensor inputs. air mass, engine temperature, RPM, and throttle position. Direct injection systems operate at 100 to 300 bar, spraying fuel directly into the cylinder for precise placement and better vaporization, which supports higher compression ratios and improved efficiency. Port injection, which sprays into the intake port, is simpler and less expensive. Some modern engines run both simultaneously. Port injectors keep intake valves clean. Carbon buildup is a known direct injection problem, while direct injectors handle primary fuel delivery. Fuel pump. The fuel pump moves fuel from the tank to the injectors at regulated pressure. Most modern vehicles use an electric pump submerged directly inside the tank, a design that uses the surrounding fuel to cool the motor. Pump pressure varies by system. Port-injected engines run around 3 to 4 bar, while direct injection systems require a low-pressure tank pump feeding a high-pressure mechanical pump on the engine, which builds to 100 bar or more. A failing pump announces itself gradually: hesitation under load, hard starting, or the engine cutting out at high throttle before eventually failing to prime the system at all. Spark plugs. In a gasoline engine, the spark plug initiates combustion. A high-voltage pulse jumps across the electrode gap, typically 0.6 to 1.1 millimeters, creating an arc that ignites the compressed air-fuel mixture. The ECU calculates spark timing precisely based on engine speed and load. Advance it too far and detonation occurs. Retard it and efficiency drops. Plug materials have evolved significantly. Copper plugs are inexpensive but wear quickly. Platinum and iridium tips maintain a consistent gap as they erode and are rated for 60,000 to 100,000 miles. Cold plugs dissipate heat rapidly and suit high-output engines. Hot plugs retain heat to self-clean, better suited to low-load conditions like city driving. Ignition coils. A spark plug needs 20,000 to 40,000 volts to fire reliably under combustion pressure. The ignition coil generates that from the vehicle's 12-volt electrical system by electromagnetic induction. A primary winding collapses its magnetic field into a secondary winding with a turns ratio of roughly 1 to 100. Modern engines use coil-on-plug design, where each spark plug has its own dedicated coil mounted directly on top of it. This eliminates distributor caps and plug wires, delivers a stronger and more consistent spark, and allows the ECU to fire each cylinder independently. A failing coil typically causes misfires on one specific cylinder, a rough idle, reduced power, and a check engine code pointing directly at the affected cylinder. Combustion chamber. The combustion chamber is the enclosed space above the piston at top dead center, bounded by the piston crown, cylinder walls, and the recess in the underside of the cylinder head. This is where the chemistry happens. The air-fuel mixture ignites, expands rapidly, and drives the piston down. Chamber geometry is carefully engineered for fast, even flame travel. A compact, centrally sparked pent roof or hemispherical chamber reduces detonation risk and improves thermal efficiency. The compression ratio, total cylinder volume divided by combustion chamber volume, determines how much the mixture is squeezed before ignition. Higher compression extracts more energy from each combustion event, which is why naturally aspirated performance engines commonly run ratios of 11 to 1 or higher. Exhaust manifold. Once combustion is complete, the exhaust manifold collects spent gases from each cylinder and funnels them into a single outlet leading to the rest of the system. Cast iron manifolds, still common, converge runners quickly and prioritize durability. Performance headers are tubular steel and are designed around scavenging. The pressure wave from one cylinder's exhaust pulse helps pull gases from the adjacent cylinder, improving flow. Equal-length headers, where every runner is the same length from port to collector, are the standard for balanced scavenging across all cylinders. Getting tube diameter and length right for a specific engine's RPM range can meaningfully improve power without changing anything else about the engine itself. What parts did you not know before? Comment below. Hit like and subscribe. The algorithm already has your next one queued up. Just click.